Hello everyone, welcome back to another episode of Solving LEETCODE question. The question today is search in rotated sorted array. Given an integer array nums with distinct values sorted in ascending order. First, we'll rotate the array at an unknown pivot index k such that the resulting array is nums k plus 1 all the way to nums n minus 1, then back to nums 0, nums 1 to nums k minus 1. For example, if the sorted array is 0, 1, 2, 4, 5, 6, 7, and we rotate it at pivot index 3, then the resulting array would be, starting from index 3, 4, 5, 6, 7, 0, 1, 2. Now the question is, given the array nums after the possible rotation and an integer target, return the index of the target if it's in nums, or -1 if it's not in nums. And we must solve this in O log n time. For example, if nums is 4, 5, 6, 7, 0, 1, 2, and the target is 0, then we would output 4 because 0 is found at index 4 of the array. Let's look at a second example. Nums is 4, 5, 6, 7, 0, 1, 2 as before, and target is 3. 3 is not in the array, so the output is -1. How do we solve this question? Pause here if you like to think independently for a moment. To summarize the problem, all we need to do is to find the element inside the array and return its index, and we have to do it in O log n time. If the array is sorted, we can use binary search. However, the array we're given is almost sorted, but rotated at a pivot. So we probably have to tweak something in our binary search algorithm to address this. But as a first step, let's review binary search. To do a binary search, we first go to the middle element of the search range. If the target is greater than the middle element, that means it belongs to the right half of the range. So we reduce the search range to the right half. If the target is smaller than the middle element, then we reduce the search range to the left half. And we repeat step 1 to 3 until the target is found. Since each time we're halving the length of the search range, the time complexity is O log of n. Let's run through an example here. If the numbers are 0, 1, 2, 4, 5, 6, 7, they're sorted in ascending order. We'll start from the middle element, which is 4. Since the target 0 is smaller than 4, that means we go to the left side and do our search again. So pick the middle element 1, and 1 is still greater than 0, so we once again reduce the search range to just 0. And this is how we found the element. This is a Python code for the binary search algorithm. Depending on how we want to handle the edges, the code might look a little different. In our case, we set the left edge as 0 and right edge as length of nums, which is one step further from the rightmost element of the search range. And this also means when we're calculating the middle element and there are two options to consider, the right one will be picked. Just to give a very simple example, if the array is 1, 2, 3, 4, left would be 0, right would be 4, and the middle index would be 2, and that is 3 here. Now that we're pretty comfortable with the basic binary search, let's handle the special cases due to rotation. The key point here is that the target might be on the other side of nums mid due to the rotation. Look at the following two cases here. In the first case, target is 0, and let's say we're at the middle element 6. Since 6 is greater than 0, normally we will look at the left side. However, in this case, 0 has been wrapped around to the right side. And how do we know that? Because if we look at the first element, 2 is greater than 0. And this means if there's anything that's smaller than 0, it would have been wrapped around to the right side. So instead of looking to the left, we look to the right. Let's look at the second case. Say the target is 6 and we're at the middle element 1. Since 6 is greater than 1, normally we would look at the right side. However, if we look at the last element of this list, it's a 5, and 5 is smaller than 6, which means that if there's anything that's greater than 5, it would have been wrapped around to the other side of the array. So we should instead go to the left. So what we just did is essentially identifying two cases where instead of following the normal binary search procedure, we go the other way because we've identified a wraparound in the array. Let's put this into code. The setup of the algorithm is still the same, but now we have to handle the special cases first. Case 1 is when target is smaller than num0 and smaller than num's mid. This means that the target is possibly wrapped to the right, so we go to the right. Case 2 is when target is greater than num's -1 and greater than num's mid. And this means the target is possibly wrapped to the left side. So we go to the left side. And otherwise, we'll proceed with the normal binary search processing. Since we're still reducing the search range by half each time, the final time complexity is O log of n as required, and the space complexity is O of 1. And this is how we solve this problem. That's it for today. Let me know if you have any questions, and see you next time.